what is this world we live in? Does 1 second always last 1 second? And does 1 yard always measure 1 yard? Is it possible to travel through time or faster than the speed of light? These are some of the questions we're going to discuss in today's video. I'm going to tell you about the theories of relativity by Einstein. But you don't need to worry if you have no knowledge of physics. You're not going to need any to understand what follows. Just an open mind and a bit of common sense. So it's now time for you to relax, to adopt a comfortable position, because we are about to begin a long trip through time and space that might forever change your understanding of the world. And our story begins by the end of the 19th century, more than 1 century ago, when physicists, trying to precisely measure the speed of light, made a weird discovery. You know that speed, velocity, is always defined with a distance, space, and time. For example, you can be in a train moving at 100 miles per hour. But what we generally forget to precise in our everyday life is that the speed is always relative to something. In the case of a train, the 100 miles per hour are on the surface of our planet. The reference is the Earth. But if we were looking at the same train from another standpoint, for example from the Sun, the speed of this same train moving at 100 kilometers per hour on the Earth would be very different, because the Earth itself is moving, revolving around the Sun very quickly. And the same way, if there was a second train moving at, let's say, 80 miles per hour in the same direction, the speed of the first train relative to the second one would be only 20 miles per hour. If the two trains were moving at the same speed, and if you were in one of the two, it would look like the other train is not moving relative to you. But when physicists measured the speed of light in various situations, they realized that, very weirdly, light didn't seem to obey these same rules that applied to the calculation of speed. To understand it, let's take another example. The speed of light is 300,000 kilometers per second. So now imagine you are on the top of a hill, looking at rays of light passing in front of you. You're not moving, so the relative speed of light to you, the observer, is 300,000 kilometers per second. And now, let's say you board on a plane and start flying in the same direction as the light. If we follow the same logic as in the example with the trains before, the relative speed of light to you should now be 300,000 kilometers per second minus the speed of the plane. And if we imagine the plane was flying at light speed, the relative speed of light to you would now be 0, and you should be light, standing still, not moving, relative to you. But the problem is that it doesn't work this way. Whatever speed you're going to adopt, light will always go at 300,000 kilometers per second relative to you. And this, given the laws of physics as they were understood until the 19th century, made no sense. It looked absurd. It is not possible to figure out, to imagine how light can always have the same relative speed to you, whatever your own speed can be. And on this paradox, a man called Einstein is going to begin to elaborate a theory that will change forever the face of science and our understanding of the world. Until the beginning of the 20th century, the assumption in physics was that time and space were stable, constant, absolute, that they never changed. But if this was true, how to understand, like in the example given before, that in the same time lapse, light could cross a different distance depending on the observer moving at the same speed? It's impossible. And that was Einstein's first intuition. He supposed that maybe time and space, that for centuries in Western physics and for millennia in the history of man had been supposed to be constant, were not constant and might be able to vary. His first discovery was that move and velocity affect the passing of time. That seems almost impossible to conceive given our sensible experience of the world, because we are used to very slow speeds. But half a century after the publication of Einstein's first theory, an experiment clearly proved that this was right. Speed modifies the passing of time. In the 1950s, the first atomic clocks had been invented. These are clocks that are incredibly precise, much more than the mechanical ones that are still in use today. And the scientists took two atomic clocks with exactly the same settings and kept one on the ground, put the second one on a plane. The plane took off and flight for a few hours before landing. Before the flight, the two clocks were perfectly synchronized, but when the scientists compared them after the flight, it appeared that time had passed slightly more slowly for the clock that was put on the plane. The proof that speed, movement, could slow down the passing of time had been made. And the implications are gigantic. We may not perceive them in our everyday life because the speeds we live with are very slow, very small in comparison with the speeds that exist in the universe. The fastest rocket ever built is able to move tens of thousands of times more slowly than the speed of light. But if we were able to build rockets, spaceships, that could move at 10, 20, 30% of the speed of light, the modification of time would become apparent and visible. If a spaceship, let's imagine that it would be able to fly at 10% of light speed, was created and left the Earth, this is what would happen as the spaceships would accelerate. For the inhabitants of the ship, time would start to slow down, even though they would not perceive it. Time would stay the same for them. But compared to what would have happened if they had stayed on Earth, their hearts would slow down, their aging would slow down. And if they returned to Earth after 1 or 2 years spent in space at high speed, time would have passed much more quickly on our planet. This means they would have traveled in time, spend 1 or 2 years in space, and they would come back 20 years, 30 years after their departure on our planet. Actually, the time machine has already been invented with this theory. The only problem is that we are technically unable to build it because we are unable to create spaceships that can fly that fast. But the slowing down of time also comes with a contraction of space. When speed increases, the object experiences a contraction of space. So once again, the astronauts would not perceive it, but compared to what it would have been if they had stayed still on Earth, their spaceship would become smaller. And there are more implications to this dilatation of time that Einstein would also think about and start to formalize, put into equations. Let's imagine that traveling at high speed, the spaceship passes in front of a planet where an asteroid is falling. A big one approaching the planet at high speed. For the inhabitants of the planet, they would see the asteroid approaching very fast before impacting the planet and leading to a lot of destruction. But for the astronauts on the spaceship, relative time would pass much more slowly on the planet because they are traveling faster, and they would see the same asteroid falling very slowly and almost smoothly exploding on the surface of the planet. And yet, despite a much slower speed, the destruction would be comparable, exactly the same as the one experienced by people living on the planet. This is a paradox because the strength, the energy liberated in an explosion depends on the speed of the projectile and its mass, its quantity of matter. For example, a bullet coming from a gun can cause a lot of destruction because of its speed and despite the light weight of the bullet itself. And if a stone falls on you at relatively slow speed, it can be painful because it's massive, it's big. In that case, how to understand that the same asteroid would cause the same destruction, whatever the speed? And Einstein answers to this too, explaining that the mass can vary, which is another revolution in the understanding of the universe, and that the mass, the matter, is just another form of energy. Hence the very famous equation E, the energy, is equivalent to the mass multiplied by the square of light speed. And this discovery implies that even in a small quantity of matter, there is a huge energy enclosed. To give you an idea, potentially there is enough energy in 1 kilogram of matter, about 2 pounds, to lift a mountain on the Earth, a big one. Initially, Einstein's theories were taken very theoretically by the scientific community until the 1920s and 1930s, when the structure of atoms started to be better understood. When physicists realized that the energy enclosed inside every atom was gigantic, the energy maintaining together the protons and the neutrons inside the core, the nucleus of the atoms, and that sometimes this energy could be partly released. This is the case in an atomic explosion, when a reaction of fission liberates a small part of the energy enclosed inside the atoms, and even more in the case of fusion, when, like in the stars, atoms of hydrogen merge to give birth to atoms of helium. I told you about that in the video about the sun. I'm going to put the link in the description below. These were the main conclusions and advances in Einstein's third theory, to be published in 1905. The relativity. It was later renamed specific relativity, because this theory was somewhat incomplete. It was intended to be a theory explaining how the universe worked, but some of the forces present in this universe were still unexplained and not put into equations. One force that is extremely important and remained absent from the theory was gravitation, the mutual attraction between large bodies in the universe, this force that makes planets revolve around stars and satellites revolve around planets. The same gravitation that makes us have a weight and stay stuck to our planet because we're attracted to it. Willing to enrich and deepen his theory, Einstein continued to work on it and came back a few years later with another genius intuition, another breakthrough, maybe even more impressive than the first ones. He understood and proved mathematically to begin with that not only speed and movement affected the passing of time and space, so did matter. That large bodies in the universe were able to modify the very structure of the universe. How to understand that? You know that there are 3 dimensions of space. There is length, width, height. But for just 1 minute, let's imagine that our universe is only in 2 dimensions. It would be just like a flat space. When you have a large body of matter on the structure of this flat universe, the quantity of matter of the body produces a curvature of this universe. We use this image of a 2-dimensional universe because we are unable to imagine, to visualize the curvature of a 3-dimensional space. Our minds are just unable to figure it out. But it speaks for itself. When a curvature of space-time appears, this modifies the orbit of planets, the orbit of satellites, and explains the gravitation. The Earth revolves around the Sun because it is forced to by the curvature of space-time that the Sun produces. And the same works with the moon and the earth, and the same works too for us when we jump and come back to the ground, attracted by our planet. Actually, we are falling in the curvature of space-time that the planet produces due to its gigantic mass. In fact, what Einstein managed to do with this second theory, the one called general relativity, because it's much broader than the first one, is that he defined gravitation. Since Newton, gravitation was known and measured as a force, but the reason why it worked remained very unclear. With Einstein, we have a form of explanation or definition of what gravitation is and how it works. And a large quantity of matter not only affects space, it affects time too. At the center of our planet, time is passing more slowly than at the surface, and even if this is absolutely impossible to measure and visualize, when we stand up, because our feet are closer to the center of the earth, time passes a little bit more slowly at the level of our feet than at the level of our head. General relativity does not affect that much our everyday lives, obviously, but still there are a few direct applications. For example, if you have a car with a GPS, you know that GPS works with satellites, and the satellites are revolving around the Earth very quickly. Due to their speed, time is passing slightly more slowly for them than for us at the surface of the planet. And in order to make the system work, the clocks on board the satellites had to be adjusted, taking into account the conclusions, the equations of relativity. Otherwise, your car with a GPS couldn't work. I believe that beyond the practical applications of the theory, it has to make us think about the limitations of our minds. We are not even able to imagine, to visualize the true structure of the universe, and maybe general relativity is just a step in our understanding of the world. Maybe new dimensions could be discovered, or maybe our human condition is too much a limitation for us to understand one day how the universe works, very much like an ant or an animal could not understand how a computer works. They just don't have the mind structure that would make it possible. Anyway, this was just an introduction, and as always, I hope you liked it, that you found it interesting. I'll see you soon for a new video, and in the meantime, I wish you sweet dreams and a lot of curiosity.